thank you to the organizers for making me give this talk. So, Fano threefolds of type 4-1. Sometimes I would wish that nobody cared about Fano threefolds of type 4-1, that we could just play together and people would leave us alone. But no, people have decided to make this Fano threefold into a nuclear test ground for all the horrors of the brave new world. So Katsarkov and Kontsevich, this August, finally they published their big nuclear weapon, which turns Fano threefolds into atoms. And after turning the threefolds into atoms, you can prove everything. So you can prove like non-rationality, which is supposed to be impossible. That's the whole point of rationality problems. And that was this August. And even yesterday they solved the problem of G-rationality. So for which groups can act on this Fano threefold and on P3 such that there's a G equivariant birational map between this threefold and P3. So these problems are not supposed to be solved. So today, let us solve a problem which is supposed to be solved, which can be solved, like classifying the groups of automorphisms of this Fano threefold. So like doing things in the right order. So there's 105 types of Fano threefolds, 105 families. Some of them are more symmetric and simple, like P3 or P1 times P1 times P1, and they have very big automorphism groups. Some other Fano threefolds are obtained, for instance, by blowing up some curves, and then the group action acts on these curves, so you have more structure and more geometry. So the group of automorphisms becomes smaller, and sometimes they become finite, for instance, in this case. So in this case, the group of automorphisms is finite, so we can make a list. There's 8 possible automorphism groups, and for every Fano threefold of this type, the group of automorphisms belongs to this list. So can people see that? So we are working over a field K, which is algebraically closed and has characteristic 0. And the definition of a Fano threefold of type 4-1 is that it is a divisor P1 times P1 times P1 times P1 of multidegree 1, 1, 1, 1. So this means that you take P1 times P1 times P1 times P1, and then you take an equation which is degree 1 in each of the P1s, and then you get a threefold. So we can write it like this: Pf V1 times Pf V2 times Pf V3 times Pf V4. And this is useful because, so V1, V2, V3, V4, they're two-dimensional vector spaces over the field K. And this is useful because it allows us to distinguish between the 4 P1 factors. And we assume that X is smooth. So this talk, now it will disappear. Like this. This talk is devoted.
This one and this one.
This talk is devoted to the following main theorem. That the group of automorphisms of such a threefold X is isomorphic to a semi-direct product between Z2 to the power 4 and the group of automorphisms of a genus 1 curve gamma, which fix a degree 3 divisor D. So gamma is a genus 1 curve. I will say a bit about genus 1 curves a bit later. And D is a degree 3 divisor. So it's 3 points on gamma which are fixed. And this group here is the group of automorphisms of this curve which fix this divisor.
It's just plane group curve.
Yes, this is just a cubic curve in the plane. And also this group here belongs to the following list. It can be trivial. It can be Z2. It can be Z3. It can be Z4. it can be Z6, it can be S3, or it can be S3 times Z3. So I promised you 8 different groups, and here we have 7 different groups. And that's because Z2 here, for Z2, there are 2 different possible actions which can appear as an automorphism group of a Fano threefold of type 4.1, and all the other groups here, there's only 1 possible action. And if X is general, then the marked curve gamma comma D is general. So the automorphism group of this curve gamma comma D is trivial, and the automorphism group of X becomes Z2 to the power 4. So it's pretty simple. It's just 4 different involutions which commute with each other. And the plan of the talk.
So is it clear in this case how this group acts on X?
Yes. So the way to understand this proof. So this curve, of course, depends on the geometry of X. So the way to understand it is first we need to introduce the geometry of X. And in particular, we will introduce 16 special points to ij, which lies in X. And then we will introduce theorem 1, which says that X has as a normal subgroup a group Z2 to the power 4. And this group acts on these points, these 16 points, transitively and freely. So these points are identified with this group. And then theorem 2. So these are more like propositions, but it's easier for my talk to call them theorems. The stabilizer, or say, let's just write it, automorphism group of X, which fix one of the 16 points, we can choose one arbitrarily, is isomorphic to this group, automorphism of gamma comma D. So this group here stabilizes one of the 16 points, and this group acts transitively and freely on the 16 points. So the action of this group here corresponds to the action of this group here on the 16 points. So that's the strategy. And one of the main points of my talk is that there's 2 different perspectives on this problem. There's the classical projective geometry perspective, and there's the moduli stack perspective. And almost everything which we're doing here can be formulated here, and almost everything we're doing here can then be translated back to some concrete geometric things we are doing. So to show how things in this world correspond to things in this world, I will reserve this part for moduli stacks. So everything here will be a bit hand-wavy when we go into this world here. But if you're not familiar with a moduli stack, in my case, it's all Deligne-Mumford moduli stacks. So a moduli stack can, on one hand, a Deligne-Mumford stack can on one hand be thought of as some kind of scheme, some kind of space whose points parameterizes the things we want to parameterize. And at each point, we have attached the automorphism group of that thing. And on the other hand, it can also be thought of as a group point whose objects are the things we want to parameterize and whose isomorphisms are the automorphisms of those objects. Yeah, so this is this one. So let us start with the geometry of X. Okay, geometry of X. So the first thing is proposition 3. So consider the map from P1 to P1 times P1 times P1. So we pick 3 out of the 4 P1 factors. Okay, this is Prokhorov and Kuznetsov wrote this down, but Loginov also did it. I'm not sure who was first, but so let us just write PF Vj times PF Vk times P of VL to say that we're projecting to these three factors and call this map pi JKL. Then the proposition says that this is the blow-up in a curve gamma I, which lies inside P1 times P1 times P1, this one here. And gamma I is a smooth genus 1 curve of degree 2, 2, 2. So for instance, if this is P of V1 times P of V2 times P of V3, we call this gamma 4. And if this is V2, V3, V4, we call this curve gamma 1.
It will be easier to name also P. Like P1 if we project on 2, 3, 4.
Pi here. Yeah, JKL.
Yeah, why would we don't order method?
No, the order doesn't matter. We could also just name it pi I, it doesn't matter.
Yeah.
It's so we denote the exceptional divisor by EI. So for instance, E1 has degree -1, 1, 1, 1. And if we take E2 exceptional divisor, then E2 has degree 1, -1, 1, 1, and so on. But this is not so important. So this proposition you can prove, for instance, by writing down the equations. But so I don't want to prove this, but this is how to consider this a Fano threefold in terms of blow-ups, in terms of minimal model program.
Yeah, and so this E1 is divisor of an locally free sheaf that we just restrict O -1, 1, 1, 1 to X and then take its divisor.
Yes.
Okay.
Right. So this is the divisor which lies in X, which is where this map is not an isomorphism. Okay. So now I want to make some definitions. So if we intersect two of the exceptional divisors, say EI intersected with EJ, we get a curve, and we denote this curve by gamma IJ. So this lies inside X. So this way we have 6 curves, gamma IJ, which lies in X, and we can also intersect 3 exceptional divisors. Then we get a set of finite points. So we define QI as the intersection between EJ, EK, and EL, which lies inside X. So we have 4 quadruples of 4 points. So QI we denoted by QI1, QI2, QI3, and QI4. So we can see it like this. Here we have Q1 is 4 points. We have Q2 is 4 points. We have Q3 is 4 points, and we have Q4 is 4 points. So these are the most important geometric objects which lie inside.
And why will be 4 points?
You can compute the intersection number. That's one argument. Or you can each of the points lie on the curves, and you can consider them as the ramification points of some puzzle covering. But that's not.
And these points, they never coincide.
They never.
Or E1.
Yeah, these are 16 points which never coincide. I don't want to prove it. Proposition 4. So we have this curve gamma IJ, which lies inside X. And we have this map pi JKL to P1 times P1 times P1. And here we have the curve gamma I. Then this map here restricts to a map which takes this curve to this curve, and it's an isomorphism. Basically, because this curve lies, in particular, it lies inside EI, and EI is the exceptional divisor of this map, and the exceptional divisor maps to the exceptional locus. So this curve maps to this curve. And then you can count the degree of this map, and the map is degree 1. So this is an isomorphism. Then we can define more isomorphisms phi ij, which goes from gamma I. Then we take the inverse of this map, so we get a map to gamma ij. And then we take the map to gamma j. So this is an isomorphism. So it looks like
Because they are full isomorphic to intermediate Jacobian, right?
yes, but not canonically. Phi ij is the same as phi ji inverse. So we have all of them.
Because they are not even correct. Right?
Yes. So gamma 1 is isomorphic to gamma 2, which is isomorphic to gamma 3, which is isomorphic to gamma 4. So it looks like it's the same curve. But the thing with genus 1 curves is that they're very, very slippery. Usually you know genus 1 curves as elliptic curves, a cubic curve in the plane. But a cubic curve in the plane, you also always have a point fixed on the curve. So you have some structure fixed on the curve. With genus 1 curves, we love to fix some structure, fix some divisor, fix some involutions on the curve, or fix some embedding into some projective threefold, because it gives some structure on the curve. Without any structure, a genus 1 curve, because it's so symmetric and has so little inherent geometric structure, it's very, very slippery. If you have two Fano threefolds which are isomorphic to each other, it makes some kind of sense to say that it's the same Fano threefold, some sense. If you have two genus 1 curves which are isomorphic to each other, it makes less sense to say that it's the same genus 1 curve. You want to add some structure to it. So let me show this here. So it looks like they're the same. But if we draw the data which we have in a tetrahedron, so we can draw in a tetrahedron, we have 4 vertices. So we can draw the 4 curves at the 4 vertices of the tetrahedron. So we have gamma 1, gamma 2, gamma 3, and gamma 4. And then we have an isomorphism between gamma 1 and gamma 2 from this phi 1, 2, and phi 2, 1. We have an isomorphism here, an isomorphism here, 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 and here. But if we fix a curve, and then we take a face, and we take the composition of isomorphisms coming from going around a face of the curve. So we take the isomorphism from here to here, here to here, and back here. This would be a non-trivial automorphism, an involution of this curve. So let me write it. We define gamma ij as the map where we start with the curve gamma I. And then we take the face which lies opposite the jth vertex. And then we take the 3 isomorphisms coming from walking around that face. And it turns out that the direction doesn't matter. So we have map from gamma I to gamma k to gamma L, back to gamma I from these phi's. Then
Gamma ij.
uh,
What is the notation? Gamma ij.
gamma ij, small gamma I.
But it depends on k.
So J, it's a vertex, and then K and L, it's the curves which lies in the face, which is opposite the jth vertex.
Okay.
Sorry. Then proposition 5. Yeah, so proposition 5 says that if we take the curve gamma I and we take the map to P of Vj, so gamma I lies inside P of Vj times P of Vk times P of Vl, and we can project it to P of Vj. So this is a degree 2 map. Then the covering involution of this map, the involution of this curve, which just swaps every fiber with the other fiber, is equal to gamma ij. So, and as a corollary, this means that gamma I quotiented by this involution gamma ij is canonically isomorphic to P of Vj. So we started with our threefold X, then we obtained this, packed all the information about the geometry into this tetrahedron. And then we took one of the vertices and the 3 involutions and got, say, we can take the 4th vertex, gamma 4, and these 4 involutions, 3 involutions. 2, gamma 4, 3. Then proposition 6. Proposition 6 says that X can be reconstructed, from this marked curve, gamma 4 and these involutions, these two involutions. And let me just very quickly outline the proof because it's a bit, it's pretty nice. So we have a map from gamma 4 to gamma 4 quotiented by gamma I1, which is just the quotient map. And this is isomorphic to PFV1. And we also have a map, similarly, we have a map to PFV2 and to PFV3. So we have a map from this curve to the product of these P1s. And then we just blow up the image and we obtain the original threefold. So actually, what I've written is less strong than what I have actually proven, because this is actually an equivalence of groupoids. So if we consider the modular stack or the groupoid of Fano threefolds of type 4.1 together with an ordering of the P1 factors. So we have ordered the 4 P1 factors plus ordering of P1 factors. Then this is the same as the groupoid or the modular stack of genus 1 curves gamma 4 with 3 fixed involutions. So all the geometric structure of X is encoded inside this curve and these 3 involutions. And in particular, if you want to understand the automorphism group here, so the automorphism of this guy is the automorphisms of X which respect the ordering of the P1 factors with X trivially and the PK group. That automorphism group is equal to the automorphism group of this guy, and the automorphism group of a genus 1 curve with 3 fixed involutions is equal to the set of automorphisms of the curve gamma, which permute with each of the 3 involutions.
What do you mean by ordering of P1s if you just have a geometric threefold?
So in particular, so we fix X and we pick an ordering on the P1 factors. So if you
do just have format from X to P1.
Sure, this is one way to do it.
Okay. And to order your 4 element.
Yes. Okay. And the automorphism groups here of these objects are just the ones which respect the ordering. Okay, so now we already can find some automorphism groups of X, because we need to find some automorphism group of X. It's enough to find some automorphism groups of a genus 1 curves which commute with 3 involutions. So what could be some example of such automorphisms? If somebody know about automorphisms of genus 1 curves.
What happens if you take all their involutions as identities?
They have to be non-trivial and they have to be pairwise distinct.
Okay.
So it's not a compact modular space because we're not considering singular Fano threefolds. Okay, so I don't have that much time, so let me just say we have so-called 2 torsion translations. And when we're working over an algebraically closed field, this gives us set 2 to the power of 2. So this gives us 2 of the involutions from here. And the other involutions comes as follows. So to get the modular stack of all Fano threefolds from this stack, we just take the quotient by S4, which acts here by permuting the ordering of the P1 factors. Then we get a modular stack of Fano threefolds of 4.1. And we get an equivalence. So S4 acts here. So via this equivalence, we obtain an action here, and we can take the quotient. So it's the same thing as here by S4. So this is an S4 quotient. And S4, we have a short exact sequence 0 to S3 to S, no, sorry, set 2 squared. to S4 to S3 to 0. And morally, the Z2 squared here inside S4 acts here by sending an object, a marked curve, to, I don't want to say self, but to a marked curve which is non-canonically isomorphic to itself. So it takes an object here, sends it, this group here, sends it to an object which is non-canonically isomorphic to itself. So basically what this group here does is that if you consider this as a category, it just adds isomorphisms to this category. So this subgroup here just make the automorphism groups bigger. And that is how we get the other two set involutions here. And morally, so this is a semi-direct product. So in,
And the quotient permutes three involutions.
yeah. So there's three here, it just permutes the three involutions. And what does this mean? It means that we have the following technical lemma. Okay, so this follows from the moduli stuff, so I will delete this. So we have a technical lemma. So this technical lemma both follows from this moduli stuff, but it can be translated into concrete geometry and can be proven with no stacky stuff. It means that automorphisms of X are in bijection with the set of pairs sigma, G, where sigma is a permutation inside S4, and G is an isomorphism from, say, gamma sigma 4 to gamma 4. And then we need to, before we had the condition that gamma had to permute with the three involutions, here this condition will be translated to that gamma times sigma 4 sigma j is equal to gamma 4j sigma gamma. So that
So what is sigma?
it's an element of S4. So an automorphism of X corresponds to the following data. It's determined by the following data. One, a permutation, and two, an isomorphism of genus 1 curves. And this sigma here, it's just because an automorphism of X somehow permutes these P1 factors. And the sigma is the same as the induced action by permutation on these 4 P1 factors. And then the isomorphism G comes from taking P of V of sigma 1 times P of V sigma 2 times P of V sigma 3 and sending it to P of V1, V2, V3. And this restricts to an isomorphism from gamma sigma 4 to gamma 4. That's geometrically how this G here is obtained. So it cannot be written down very explicitly, and it can be converted back from these stacks to here. But if you know like categories, the automorphism groups in this groupoid, which is the quotient, it should be equal to something which looks like this. Okay, so now we can go to the third topic, understanding the group of automorphisms, which fixes this degree 3 divisor. We need to check the time. What? That's perfect. And this following, but I don't need to do it. So, yeah, we want to describe the group of automorphisms of X, which fix a point Q 4, 4. So we want to understand isomorphisms from X to X, such that f of Q 4, 4 is equal to Q 4, 4. And this Q 4, 4 is a point which lies inside E1 intersected with E2 intersected with E3. And this F here corresponds to some sigma and some P here. So sigma, it's about how if X and permutation these 4 P1 vectors. And because F has to preserve Q44, so it has to preserve the union of these 3 exceptional divisors. So F can permute the 3 exceptional divisors, but it has to fix the exceptional divisors E4. And this means that sigma of 4 is equal to 4. So F here can permute 3 of the vectors. These 3 vectors it can permute, but this vector here, it has to fix. So we can draw this diagram. We have X, and then we have this isomorphism from X to X. And then we have the projection I 1, 2, 3 to PFV1 times PFV2 times PFV3. And we have this projection here. 1, 2, 3, P1, 3. And then so this is a proposition. This is not trivial, but it can be proven that there must exist an isomorphism from P1 times P1 times P1 to P1 times P1 times P1, such that this diagram here commutes. The 3 P1 factors can be permuted with each other, but so they have to be mapped to each other in some order. And here we have gamma 4, and here we have gamma 4. And E4 here is mapped to gamma 4, and E4 here has to be mapped to E4 here. So this map here must carry gamma 4 to gamma 4. So this is the map G. This is the same as this map G here, geometrically. So this means that the group of automorphisms of X, which fix the point Q44, is equal to the, or isomorphic to the group of automorphisms of P1 times P1 times P1, which fix this curve gamma 4. And one thing also must be fixed in P1 times P1 times P1, in the image of Q44. So Q44, it lies inside X, it maps to a point here. And to get an automorphism from X to X, which preserves this point, we need an automorphism of P1 times P1 times P1, which fixes both this curve and this point. So we find 1, 2, 3 of Q44. Okay, so now we just need to understand this group here. To understand this group, we need to understand the geometric relationship between this curve and this point inside P1 times P1 times P1. So let us draw P1 times P1 times P1. So we have the point here, Q1, 2, 3 of Q44. So this is a point. So we have a point here. If we have a point here, we have 3 distinct lines passing through that point, because we can vary this, the coordinates here, we can vary the coordinates here, or we can vary the coordinates here. So we have like a line L1 here, line L2 here, and a line L3 here, passing through our point. So let's draw the point here, and let's draw the curve gamma 4. Yeah, gamma 4 here. Then it turns out that these 3 lines, each of them intersect the curve gamma 4. So we have 3 points. We have P1, P2, and P3 on the curve gamma 4, which are just intersections between this line and this curve. So when we have an automorphism of P1 times P1 times P1, which both fixes this point here and this curve here, then it permutes these lines via the same permutation as this sigma here. So the sigma acts only on 1, 2, and 3. And this action is the same as its action on these 3 lines. And that action is the same as the action on these 3 points on the curve. And this is why the automorphism group of P1 times P1 times P1 fixing both the curve and these 3 points is the same as the automorphism group of the curve gamma 4, fixing the divisor D, which is equal to just D1 plus D2 plus D3. So this means that the points are allowed to be commuted between each other, but the union of those 3 points must be fixed. So this was theorem 2, and we have also theorem 1. So we have a normal subgroup of the automorphism group of X, which acts transitively and freely on these 16 points. And we have the stabilizer of one of the points. And using these 2 theorems, it can be proven that the group of automorphisms of X is equal to this semi-direct product between Z2 to the power 4 and the automorphism group of this curve, which fits this divisor. And yes, I have 10 more minutes. So now I would like to draw all the final threefolds. So before now using geometry, we started with the final threefolds. We obtain a curve gamma with 3 fixed points. Essentially, here we have a stack here. And this stack here is pretty interesting, but it's not the stack, but it's a bit complicated. But if you just look at the module space over the counted points, so we just look at the points of this module space. Then that is the same as the module space of these functions with 3 other marked points. So so we have the module space of these 1 curves with 3 points, and then we take the quotient by S3 because we don't care about the ordering of the 3 points. And then we get this module space, which is denoted by like this. This 1 curves with 3 unordered points. So I don't know. Does somebody have some idea what is the dimension of this module space? So we fix a genus 1 curve, and then we fix 3 points on the curve. Yeah. So it feels like it should be 4-dimensional because the moduli space of genus 1 curves is 1-dimensional. It's determined by the J invariant. And then for each point you fix, it feels like you should add a dimension. But remember in the beginning, I said that curves are very slippery. So the point is that when you add a point to the curve, you immediately lose it because it's totally symmetric. So actually this thing is 3-dimensional. You lose a dimension because first you have this curve with nothing fixed, then you fix a point, and then you immediately lose the information, but now you have something which is more fixed, and then you add the 2 more points. So something 3-dimensional. So the objects here, it's both determined by the isomorphism class of the curve, that's some constant, and it's determined by the geometry, the geometric configuration of these 3 points on the curve. So, and it's a 3-dimensional moduli space. So inside this moduli space, we have 2 surfaces. One surface where the J invariant is equal to 0, and one surface where the J invariant is equal to 1728. And that is because when the J invariant is one of these 2 numbers, the curve becomes even more symmetric and you get even more automorphism groups. That is why these 2 surfaces are important. Okay, so if you take, so you have this curve gamma and you have these points D1, D2, D3. If the curve is general and the 3 points are general, then the automorphism group is trivial. And the automorphism group of X is just a 2 to the power of 16. So if we choose a random point here, then the automorphism group of X is a 2 to the power of 4, has order 16. But you have a surface inside this moduli space of points where 2 times D1 is equal to D2 plus D3. So this corresponds to the cubic curves where you fix 1 point at infinity and 2 points are symmetric with respect to each other. In this case, you have automorphism group of the curve, which is the 2, which is just a 2. You have this involution here. And the automorphism of group group of X. Here, the automorphism groups of Fano threefolds of type 4-1 corresponding to points in the surface will have automorphism group of order 32. And inside the surface, you have Fano threefolds which are even more symmetric. Curves, marked curves, which are more symmetric. You have this curve, which corresponds to the marked curves, where, so this is our gamma, where D1, D2, and D3, they satisfy that 2 D1 is equal to 2 D2 equal to 2 D3. Here, the automorphism groups of the marked curve jumps to S3, and the curve will have automorphism group of order 96. And you also have a curve of a one-dimensional curve of Fano threefolds. So yeah, so this thing here, the curve which lies here, it should be that D1 minus D2 is equal to D2 minus D3 equal to D3 minus D1. That is this curve here, and this curve here is this one. Sorry about that. And if you are somewhere general here, the automorphism group will have order. So you have both involution, you have an involution here, which is fixed, and that is actually the only one. So automorphism group of X here jumps to 32, except for when the Jane variant becomes 0 or 728. Here, the automorphism group of the marked curve is set 2 to the power of 6, set 6, and here it's set 4. So these two are special. And you also have a curve inside this, inside the surface of Fano threefolds, which also have bigger automorphism groups. And you have one here whose automorphism group. Here we have a X whose automorphism group is the biggest possible. And this one's automorphism group is equal to S4 times A4. So it has order 288. And all the other Fano threefolds have automorphism group at most half of this. So this is the geometric picture. So I still have. Yes, I know.
They're all embedded here, but not like canonical there. But all the Martin groups of X embed in such, but not canonical there.
Embed in S4 times A4. So I haven't figured this out. It's an interesting question. If they embed canonically, but I haven't proven this. No, the blue condition here, this is the same as D1 minus D2. If we subtract this one here and we subtract D1 there, it's equal to D3 minus D1.
In the complementary. One that have like the involution which flips it, the other one you have a fixed involution which flips it, then the marked point.
Yes, so actually this curve will never intersect with this surface here. Yes, so yeah, I finished 4 minutes early, but
Then I can ask a very stupid question.
yes.
Can you remind me why that originary was going to have
So the automorphism group of the marked curve is trivial. We have no automorphisms of the curve gamma and D1 and D2 and D3.
Yeah.
So we have the semi-direct product.
Oh,
So this one is
it's
trivial.
not the curve.
Yes,
Yeah.
so we still have this group here, set 2 to the power 4, which came from these two involutions here and came from two torsion translations.
Mhm.
But we don't have any automorphism groups coming from the stabilizer. Yeah.
Even though it's not possible, the way actually found this the
So you mean how the Galois group connect?
yeah, these like on the like purely geometric particle, little particle.
So that's a good question. I need to be a little bit better at Galois cohomology and computing these cohomology classes. But as an example, you can take the weight restriction of P1 along a degree 4 field extension. And yes. So you can get some of. Yes.
You are automatically at naturally from the intermediate Jacobian, right? And the canon the canon is this one, right?
One second.
It should be. The intermediate Jacobian is a really big flow, right?
Yes, yes.
And I think
But it can act by involution, it can act by two torsion translations.
not translations. You see, intermediate Jacobian, as I didn't correct.
Yes.
You see, once group acts on the variety, the same group acts on the intermediate Jacobian.
Yeah.
As I didn't correct.
Yes.
So your group should be in the English should be probably pure.
Probably yes.
And I think that this equation.
So the only other possibility is that it acts by involutions. Oh.
If you write in general, then you can prove there's no any
It has involutions.
involution. Yeah, but it's not substitution.
Yes, yes.
And another question. You project your variety to P1 to get the integration into the best of the V6, right?
Yes.
The best of the V6 is 2A.
Yes.
And there is natural evolution of particles. So isn't your evolutions?
But it can't be those because you're fixing one of the P1s. You mean if it's one of the two torsion involutions? Probably it is. So you have so you have a map from X to P1 and you have 4 singular fibers. No, wait, no, because it acts. I don't think so because it has 4 singular fibers, and it's more like it acts in the double cover of P1 and these 4 points. So it's more like it permutes the fibers. It does. I don't think it fixes any of the fibers.
I know.
Because
on P1.
Because we have a double cover of this P1, and it's the intermediate. It's a torus under the intermediate Jacobian, and it's gamma 1, and it acts on this gamma 1 by 2 torsion translations. So we should act on this P. We have this at 2 involutions, which fixes the Picard group. They act on each of the P1 factors non-trivially. Basically, you have P1, and then you have you have 6 harmonic points, so that these are harmonic, these are harmonic, and these are harmonic. And then it acts by the involution, by this involution, by this involution, and by this involution. So it only fixes
There are several
fixed points.
Several ways to find 4 involutions in your group. Maybe
The other ones don't fix any of the P1 factors. So there are some fibers which are fixed. So and probably those fibers. So you can't look at all the fibers will not be fixed, but some fibers will be fixed. So if you look at that fiber, then probably you're right.
there is some strange things here. Because still, I think that we have such an evolution. Because fibers are toric, so toric varieties.
So some fibers are mapped to other fibers, and some fibers are fixed, and probably on the fibers which are fixed, you're right. But if the fiber is not fixed, then
Now this the most symmetric one of threefold. Can you write the equation in P1 times P1 times P1 times just sum of x I, you know.
I can't write the equation, but I can describe how to obtain it. So you take what?
Some example.
Some x1, y1, xi, yy, and so on. Linear combinations.
Yeah, but it would be singular, no?
No, the sum of such guys.
You think
Linear combination of
xi, what?
yj, zk, and t, and yeah. Yes. Maybe some coefficient. It's a general equation.
How does the A4 act? I see how S4 component acts by permuting x, y, z, w. But how does A4 act?
A4.
Yeah.
By the multiplication.
By what?
Открутка на мнимую единицу.
Откуда А4?
Это произведение, это на самом деле сплетенное произведение, это как бы механическое разложение.
Там нет А4?
Нет, там есть А4, но ты можешь его переразложить, А4 в полупрямое произведение и взять другое сечение.
Нет,
Да.
для общего у вас это просто авиагруппа.
Не, ну вот я вопрос про самый симметричный.
Это не самый симметричный.
Так.
Он не написал самый симметричный.
So I can explain geometrically how I obtain it. So I take genus 1 curve gamma with k invariant equal to 0, and then on that curve you can take, if you pick a point on the curve, then there are exactly, so here it would be this inflection point, no, not like that. So the curve would be written like y squared equals x cubed minus 1. So if you want homogeneous coordinates like this, and then on the line x equal to 0, you have 3 inflection points such that there is an order 3 automorphism of the genus 1 curves, which preserve each of the 3 points. And you take d1, d2, d3 to be these 3 points on this line.
You don't know the equation. Only this construction.
No,
Okay.
but it should be,
Okay.
it shouldn't be that hard to
Yeah,
write
okay.
it down, because then you take the projection away from here and from this point and from that point, obtain an embedding into P1 times P1 times P1. Then you blow it up.
Okay.
And then you obtain x. So it shouldn't be that hard to write down the explicit equation. All right.
Be careful to write down some normal form, like Weierstrass form.
But so Chelsea has this program where he has, so far he has found these automorphism groups with equations. But probably he will also find the other automorphism groups with equations eventually. So yeah, to avoid too much intersection, I try to not do any equations.
Because of this, yes.
Yes. To avoid any overlap. So if